transistors. And then from Wednesday this week, we are going to continue discussion on the JFET, junction field effector transistors, and then silicon MESFET and gallium arsenide technology, and SOI and thin film transistor. Silicon on insulator. And then we're going to finish the class of this semester. All right? And then we have to decide the final One is today is Monday, Tuesday. Today is what? 28th. 29, 30, 1, 2, 3, 4, 8, 7. How about have a final on the 7th?
Professor, I have taken your class 응용전기 화학 특강하고 반도체 로봇 기술자. I think these two they are all ended by in papers. And we give some papers and we write a report and something. Can we take this as a final exam this time?
Well, that's the one way. You suggest to have a final exam and a written paper submission and special topics, things like that. Huh? You want to have a take-home exam? Take-home exam? Well, that's one way to do this, the final. I'll think about it. Okay. And if it's an in-class exam, of course it's an open book, open note, everything is open. Okay. So let's have a final anyway on the December 7th. Okay. That's all right. Today we continue the bipolar transistors, and especially we want to discuss about the saturation mode. Okay, when we set the stored excess saturation charge. We normal operation condition is emitter base voltage is forward bias and the base collector we set reverse bias. That is the normal operation conditions. But in a saturation mode, we set emitter base forward bias, but we set the base collector also, we apply the forward bias to this. And then what's going to happen is that when you increase the bias, then the current is going to go like this. This is a emitter and a base. Slope. But when you have beyond the saturation, then what's going to happen is that you keep this slope, and then we have some, we call the charges, saturation charges, with the same slope. Same slope. Okay, that means base current, and let's see. Let's say the beta F is 50 and the tau F is 0.1 nanosecond. So the tau BF is going to be 5 nanoseconds. Okay? It's a multiple of these two terms. Beta R is 3 and tau R is 1 nanosecond. And then the BR is going to be 3 nanoseconds. Let's suppose that we have a system something like this, okay? And then when the base current is 10 microamps, then the current is going to be 0.5 milliamps in this case, which means IC is beta F IB, okay? So it should be something like this. And when the base current increases to the 50 microamps, then of course it's going to be 2.5 milliamps. And 100 microamps, it becomes 5 milliamps, okay? And then 200 milliamps, or microamps of base current is 10 milliamps. Now, if you increase the further 500 microamps, you still have 10 milliamps because it is saturated. You don't have any current anymore beyond this. So we can set this as a saturation. Okay? So it's supposed to be 500 microamps, and then the base current saturation now is 500 minus 200, which is going to be 300 microamps. Okay? So we define for this observation, we just define Now, the saturation charges as charge F that we have discussed and charge R, the total charge, and then minus charge F at edge of saturation. Okay? And then accordingly, we just set the current IB total minus IB edge of saturation. Okay, we just define this. And then we can set the base saturation current is going to be QS over tau S. We continue the notation here. And at the steady state, we can set IBS saturation current is going to be QS over tau S plus, this is a DC term, plus dQs over dt. This is a time-dependent term. Okay? So what we are talking about here is the stored excess charge now becomes QS is going to be tau BS times IBS times tau S by definition. And then we are going to have, in this situation, we have some extra charges on this bipolar transistors by applying the forward bias on the base collector and base emitter. Okay? And then QS over tau S and plus dQs over dt, the time-dependent term, and IBS before the signal, then IB1 minus IC saturation over beta F. Okay, this is an extra current from the edge of saturation, okay, and then B2 minus IC saturation over beta F. So basically what this says is that this, the base current is supposed to be collected current and divided by the gain for the bias. But when you have the extra stored charges, then we have an extra current which is beyond this this equation. Okay. So let me give you the example. When you have 5 microamps and then you increase that to 10 microamps, something like this, at the time t1. we start out with the equation IBS is equal to QF over tau BF plus dQF over dt. And then we solve this the first differential equations in terms of the QF. Okay, QF is IBS tau BF minus tau BF dt over dQF. That is the solution of this the first order differential equation. And we know the charges initial charges is going to be IB1, that is the B1, and that is the IB2. And then you set, we have a system like beta F is 50 and tau F is 0.1 nanosecond and tau BF is equal to beta F tau F and then 5 nanoseconds, something like this, okay? Then you just plug these numbers into this equation, you end up with 25 picocoulombs. And then QF infinity, after you're changing to 10 microamps, then the equation is going to be something like this, so that you end up with the charges of 50 picocoulombs. And you solve this equation, and the QF now, the general solution is going to be T over tau F plus IB2 tau BF, and then you apply this boundary conditions to this at t equal to 0, then your QF is IB1 tau BF, so that A is going to be IB1 tau BF minus IB2 tau BF and minus 25 picocoulombs. So the QF now becomes minus 25 e to the minus t over tau BF plus 50. That is the equation. And once you get the charges, then you can get the collector current from the equation QF over tau F, okay? And then you just divide that with a tau F, then you end up with 0.25 e to minus t over tau BF plus 0.5 milliamps. That is the solutions. That is the current that you're going to get from your device. This is just a simple example. Let me give you one more example, okay? That is, we change 5 microamps to the 10 microamps, but now we just take an example that you start out with the 500 microamps as a base current, and then at the time t1, you just change the polarity so that now you're going to apply minus 50 microamps. And then what is the response of the bipolar device in terms of the base current? That's what we are going to see. okay, we expect, before any solution, we expected at 500 microamps, the base current is going to be in a certain values at a steady state. And then at a time t1 here, if you change the polarities, take out the charges on the base, then the current is going to be decayed to a certain curve, and then you finally reach to the steady state and then has a steady state current at minus 550 microamps. And the task is we want to know how long it is going to take out all the stored charges in the bipolar transistors when it is operated under the base current is 500 microamps. So what is it this time is going to be? That's the one we want to calculate in this example. All right? So now we know these numbers. Okay, and then the base saturation current is going to be Qs over tau S plus dQs over dt. This is the first order approximation, as a matter of fact. First order approximation. We just set the time DC term and the AC term in here, okay? And saturation current minus dQs over dt minus Qs is equal to 0. And then Qs, as we did on the first example, just to have a general solution, Qs1 e to the minus t over tau s plus Qs2. That is the general solution of this first order differential equation. So we want to solve this equation in terms of the Qs, okay? And then we just put these numbers. IB1 S1 500 micrograms minus 200 micrograms, and QS1 is equal to 300 micrograms times 3 nanoseconds, and that is 900 picocoulombs. And this one is HO saturation. We are continuing the same example that we did on the first example, okay? We said we know this 200 microamps is the HO saturation. All right? And then IBS2 is minus 50 microamps minus 200 microamps, and then minus 250 microamps. And then QS2 now is minus 250 microamps times 3 nanoseconds, and minus 750 picocoulombs. So we have deduced the Q1, QS1, and QS2 by using the fact that 200 microamps is the edge of saturation. Then we plug this in Q1 and Q2 numbers into this equation. Then we have a solution for the QS as a QS2 S1 minus QS2 e to the minus t over tau s plus QS2. Let's say. Okay. Okay, and then 1650 e to the minus t over tau s minus 750. That is the equations. And then we have this time, let's say T2. T2 is tau s, and then 1650, 750, and then we have a number, nanosecond, 2.37 nanosecond. So this means we have a delay of this switching 2.37 nanosecond because of the charges stored beyond the edge of saturation in this device. Okay? That is the simple examples, number one and number two, to explain what's going to happen when you apply the forward bias and the emitter base and the forward bias and the base and collector, so that you have a saturation mode of your device. Then we know that we have the base current, which is just IC over beta F. And then if you have a beyond this application of the voltages, then the slope is going to be the same, but this slope is related to the current, by the way. But you do have some charges stored in your base. So when you're switching this device, then that switching has to get rid of this QS to response to the input, right? So it is very important to find out what's the amount of QS is going to be. So that's about bipolar transistors that we have discussed for in this class. And maybe you can find some interesting topics about the bipolar transistors in other literatures. So if you guys are interested in some specific topic, you just go for the literature explaining that specific topics. Okay? And this is the end of the discussion for the bipolar operations in this class. Now, on Wednesday, as I said earlier in this class, we're going to discuss about the MOS transistors, not the conventional MOS transistors, but some special transistors, including the gallium arsenide technologies and the TFTs, which is now very important transistors for especially for the display devices, especially for the AMOLED displays, you have to have a very special thin film transistors. Okay, any questions? Okay, we're going to see you on Wednesday. And don't forget, we are going to have a final exam on the 7th, okay? And then before the final exam, I will let you know what types of exams we're going to have, in class or take-home exams.